In our last section, we learned how to differentiate functions by using the limit definition of derivative. This worked out perfectly, and we were able to find the derivative of many different types of functions. But it took a lot of time, and it was really tedious, and it was a lot of symbols and easy areas that we can make mistakes. So someone's much smarter than me started looking at all these derivatives, and they noticed some patterns. And the patterns they found, they then started making some rules of differentiation. And those basic differentiation rules are what we're going to learn now. So we're going to do the same thing as we were doing in the last section, but we're just doing a little shortcut. And so we don't have to go through that limit definition every time. These basic differentiation rules are very, very important. You'll need to memorize all of these, and we'll use them throughout the year. First derivative rule is called the constant rule. This says if I take the derivative of a number, my answer is going to be 0. All right, let's look at a few examples. And in this example, we're going to find the derivative using the constant rule. So y is equal to 5. Well, then our derivative is 0. If f of x is equal to -2, f prime of x is also equal to 0. If y is equal to pi cubed, dy dx is equal to 0. Pi cubed is still just a derivative. If v of t is equal to 0, then our derivative of v of t is 0, because 0 is simply a number, a constant. Second basic differentiation rule is called the power rule. This is if you have a variable raised to a power and you want to differentiate that, you move the power to the front and you times it by the variable to one less power. All right, let's find the following derivatives. Looking at A, we want to find the derivative of f of x, so that's f prime of x. Bring the power of 9 to the front times by x to one less power. So my answer would be 9x to the 8th. To do B, I'm going to need to rewrite this radical as a fraction power. So first I'd rewrite my g of x as x to the 1/5 power. Now I use the power rule, so I'd be 1/5 x to the 1/5 minus 1 power. So that's 1/5 x to the -4/5 power. And then let's get rid of the negative exponent. And then let's rewrite this problem with radicals instead of fraction powers. A rule of thumb is if the original problem had radicals, the answer can have radicals. If the original problem had fraction powers, you can write your final answer with fraction powers. For example C, let's rewrite that. So I have a variable raised to a power. So I have y is equal to x to the -2 power. And now we're going to use the power rule. So that'd be -2x to the -3rd power. And let's get rid of the negative exponent. And so I'll rewrite this as -2x divided by x cubed. So since my original problem had only positive powers, my final answer should only have positive exponents. Constant multiple rule states that if you want to find the derivative of a constant times a function, it's equal to the constant times the derivative of the function. So let's see how this works in an example. In A, I'm going to start by rewriting f of t as 5/2t cubed. So I have a constant of 5/2. I'm going to times it by the derivative of t cubed, which we just learned in our power rule, is the same as 3t squared. And then I'm going to times 5/2 by 3. And my derivative of f is equal to 15/2 t squared. In example B, I have a radical, so let's rewrite that as a fraction power. So I get y is equal to 2x to the 1/2 power. I have a constant of 2, so bring out the constant, and I want to times it by our power rule, which is 1/2 x to the -1/2. And then we're going to simplify this down. So it becomes x to the -1/2, and then get rid of our negative exponent. So that's 1/x to the 1/2. My original problem had a radical. So my derivative of y with respect to x is equal to 1/the square root of x. And C, I have my constant of 1/2, and I'm going to times that by x to the -2/3. And then I'm going to use my power rule. Multiply our constants together. Eliminate the negative exponent by moving the x to the denominator. Now my original problem had a fraction power, so I'm going to keep this one as written with a fraction power. In D, my constant is -3/2, so I got -3/2 times x. I'm going to differentiate this by finding our power rule. Well, the derivative of x is just 1. So my answer is 1 times -3/2 or -3/2. Our next rule is called the sum and difference rule. So if we have two differentiable functions called the f and g, and we want to find the derivative of f of x plus g of x, well, that's just equal to the derivative of f of x plus the derivative of g of x. Or the same rule applies with the difference rule. So the derivative of f of x minus g of x is equal to the derivative of f of x minus the derivative of g of x. So let's look at a few examples to see how this would apply in some situations you will face in this class. In example A, we're going to take the function x cubed minus the function 4x plus the constant function 5. So the derivative of f of x is equal to 3x squared using our power rule minus 4 times, well, the derivative of x using the power rule is 1 times x to the 0, which is just 1, plus a derivative of a constant, which is 0. So therefore, f prime of x is equal to 3x squared minus 4. And that's our equation to find the slope of the tangent line at any given point on our function. B, g of x is equal to this following function. Let's start by taking that constant out. So I'm going to rewrite g of x as -1/3 x to the 5th plus 4x to the 4th minus the function x 2x cubed plus the function 3x squared minus the function x plus the constant function of 11. So our derivative of g of x using our constant multiple rule would be -1/3 times the derivative of x to the 5th plus 4 times the derivative of x to the 4th minus 2 times the derivative of x cubed plus 3 times the derivative of x squared minus 1 times the derivative of x, which is 1, plus the derivative of a constant, which is 0. So multiplying this out and simplifying, we get -5/3 x to the 4th plus 16x cubed minus 6x squared plus 6x minus 1. And we have found the derivative of g of x. All right, let's look at how we can apply this in problems like we've done in the last section. We're going to find the slope of the graph of f of x when f of x is equal to 2x squared plus 4x minus 1 at the given points. So start by finding the derivative of f of x using our rules that we've just gone over. And that gives us f prime of x is equal to 4x plus 4. And now we just simply evaluate. So for part A, if we wanted to evaluate our slope of our tangent line, slope of the graph at x equals -1, I just find the derivative at -1 by replacing every x with -1. So the slope of our tangent line, or the slope of the graph at the point x equals -1 is 0. Now we're going to try the same thing for x equals 0. So I'm going to use the same derivative equation that I just got. So our derivative is equal to 4x plus 4. This time replacing every x in our derivative equation with 0. We get the slope of the graph at x equals 0 is 4. And then finally we can do it at 2 by replacing every x with 2 in our derivative function. And I know the slope of the graph at x equals 2 must be 12. Now let's look at finding the equation of a tangent line of the graph of y equals x cubed plus 3x squared minus 2x plus 11 when x is equal to -1. So instead of using our limit definition of derivative, we're going to find our derivative using our basic differentiation rules. And we get the derivative of y with respect to x is equal to 3x squared plus 6x minus 2. And then we want to find the derivative at x equals -1. So we're going to evaluate this by replacing every x with -1 in our derivative function. After simplifying this down, we'd find out that the derivative of y with respect to x at x equals -1 is equal to -5. Now that is the slope of the tangent line, but the problem asked us to find the equation of the tangent line at x equals 1. So we have to use that slope and a point. But I only know the x value of my point, so I need to find the y value of my point. So I go back to my original equation, which was y is equal to x cubed plus 3x squared minus 2x plus 11. And I evaluate this function at -1. So I replace every x with -1. And I find that the point of tangency is x is equal to -1 and y is equal to 15. So now I have a point on my graph, which is the point -1, 15, and I have the slope of the tangent line, which is -5. So now that we have a point and a slope, we can find the equation of the tangent line. I'm going to use the point-slope form. You can use that y equals mx plus b form if you want. So substituting in 15 in place of my y1, -5 in place of my slope, and -1 in place of my x1. Simplifying this down and getting y equals. My tangent line equation will be y is equal to -5x plus 10. Next, we're going to look at finding the derivative of trig functions. And we're going to start by looking at the derivative of sine. And I'm going to explain what the derivative of sine is by using our limit definition of derivative that we've learned in section 1. So we're going to find the derivative with respect to x of sine using our limit definition of derivative. So remember, that's the limit as delta x goes to 0 of our function evaluated at x plus delta x, so that's sine of x plus delta x, minus our function sine of x, all divided by delta x. Now I notice I got sine of x plus delta x. Well, that is the sum formula of sine. So we call that sine of x times cosine of delta x plus sine of delta x times cosine of x. Then minus, we still have that sine of x on top, divided by delta x. I notice I have a sine of x and a sine of x in this first term and last term. So I'm going to rearrange my 3 terms on the numerator so that my 2 terms of sine of x are written next to each other. Minus, taking out my GCF of sine of x from these last 2 terms, get minus sine of x times 1 minus cosine of delta x over delta x. Now, cosine of x and sine of x are just constants because our variable is delta x, not x. And so I can factor out that constant from a limit. So I'm going to take that cosine of x out of my limit and have that times by the limit as delta x goes to 0 of sine of delta x over delta x, minus factor out the constant sine of x, and that'll be multiplied by the limit as delta x goes to 0 of 1 minus cosine of delta x over delta x. Hopefully these limits are very familiar to you. Remember, the limit as a variable goes to 0 of sine of x over delta x is equal to 1. And remember that the cosine formula there is equal to 0. So I know the derivative of sine of x is cosine of x. You need to memorize that. Memorize, memorize, memorize. The derivative of sine of x is equal to cosine of x. The derivative of cosine is equal to negative sine of x. And if you like to, feel free to prove that to yourself using the limit definition of derivative and verify that cosine of x is equal to negative sine of x. Let's use all our basic rules of differentiation that we've learned in this section to evaluate these three examples. Starting with example A, we have y is equal to 3 times sine of x. So that's y is the derivative is our constant times the derivative of sine, which is cosine of x. So y prime is equal to 3 cosine of x. In B, we can rewrite this as y is equal to 1/2 times cosine of x. So our derivative is our constant, which is 1/2, times the derivative of cosine, which is negative sine. So my derivative of y with respect to x will then be negative 1/2 sine of x. And for C, we'll find that f prime of x is equal to 2x plus 1 minus our negative sine of x plus our constant 2 times by cosine of x. Simplifying this down, f prime of x is equal to 2x plus 1 plus sine of x plus 2 cosine of x. Well, there was a number of differentiation rules we learned in this section. Please review over them and start memorizing them. I suggest you make flashcards and start practicing all these rules.